In this video we're going to look at curve sketching, and we're going to see how to use transformations to increase the range of functions that we can sketch. First of all, why is curve sketching so important? Well, here's an example to illustrate that. Suppose we're looking at the number of fish in a lake, and we've got a mathematical model for the population p as a function of time t. Suppose that after a lot of hard work we get to a formula for the population p as a function of time. And we want to know the answer to the question, what ultimately happens to the fish population? What happens after a large time? Now, we could extract that information from this formula. But I claim that if we have the graph over here instead, even though it's only a sketch, we can get the information that we want much more easily. We can see that if the population starts below 1,000, then it increases to 1,000. And if the population starts above 1,000, it decreases to 1,000. So in either case, after a large time, there's 1,000 fish in the lake. And while you can get that information from this formula, it's much harder to get, and it's much easier to get it from the sketch. So that's one of the reasons why curve sketching is important, that you can more easily get qualitative information from the sketch than from a formula. Curve sketching is something that many people find hard. And one of the reasons is that there's not a single set of instructions that are the same every time. However, there are some things that are important to be able to do if you are going to be able to do curve sketching. The first is to know how to sketch some common functions, and we'll look at those shortly. The second, and that's the subject of this video, is knowing how to sketch a function using a sketch of a related function, in other words, using transformations. And the third is, for more complicated functions, knowing what questions to ask to help you to sketch that function. So here are some of the common functions that you should be able to sketch confidently before you try sketching more complicated functions. So here we have sine, cos and tan, the exponential function, the natural logarithm, and powers of x. So here I've sketched x squared and x cubed, but you should know how to sketch any power of x. The first transformation we're going to look at is where the function f of x gets multiplied by a constant. And to keep things simple, that constant's always going to be positive for this video. So here we're multiplying the function values by some number a. Now if the number a is bigger than 1, then the function values will stretch out. And if the constant a is less than 1, then the function values will squash down. So here's an example. Here we have the function f of x equals x squared. If we want to sketch f of x equals 2x squared, then we have to double all the function values. So the graph stretches up by a factor of 2. So that's f of x equals 2x squared. If we want to sketch f of x equals a half x squared, then the function values get shrunk down by a factor of 2. So here's f of x equals a half x squared. So the next transformation relates f of x and f of x plus a. And because we're adding a constant onto the function values, all we do here is shift the graph up or down. So here I've traced the graph of f of x equals x squared, and if I want a graph of x squared minus 1, I simply shift that down by 1. If I try doing the same thing, but instead I want the graph of x squared plus 2, I simply shift that graph up by 2. The next transformation we're going to look at is the relationship between f of x and f of x plus a. Now this time, because we're shifting the values of x, we're shifting the graph to the left or the right. So here I've traced the function f of x equals x squared. And now what happens depends on the sign of the number a. If a is positive, then we shift the graph to the left. And if a is negative, we shift the graph to the right. So if I want the function x plus 1 all squared, a is 1 and that's positive, so I shift the graph to the left. Again, I've traced f of x equals x squared, if I want a graph of x minus 1 all squared, a is minus 1, and so I have to shift the graph to the right. And so that's a sketch of x minus 1 all squared. The final transformation involves f of x and f of a times x, where a is a positive constant. In this case, because we're multiplying x by a constant, we're either squashing the graph down or stretching it out. If a is greater than 1, then we squash the graph down. And if a is less than 1, we stretch it out. So here I've drawn f of x equals sine x, and I want to use it to sketch f of x equals sine 2x. So here a is 2, and because 2 is greater than 1, the graph gets squashed down. So here's a graph, here's a sketch of sine 2x. So it's just the sine x graph squashed down by a factor of 2. Here's the same thing, but for sine of half x. So now a is a half, which is less than 1, so that means the graphs get stretched out. So here we take the sine x curve and stretch it out by a factor of 2. So that's a little bit of the graph of sine of a half x. So in this video, we've looked at how we can use transformations to extend the range of common functions that we know how to sketch.